In this video, we will be looking at reactions of alkenes with halogens. Earlier in this chapter, we saw that alkenes can undergo electrophilic addition with HBr, and even though the hydrogen and the bromine could add either way to the alkene, the major product is this one. This is called the Markovnikov product, where the hydrogen becomes connected to the alkene carbon that originally had more hydrogens, and the bromine becomes connected to the alkene carbon that originally had fewer hydrogens. And the reason why we get Markovnikov addition is because this is the product that arises from the more stable carbocation instead of this carbocation. There are also aspects of stereochemistry when it comes to electrophilic addition, and it's because of the carbocation intermediate. Keep in mind that this carbon is sp2 hybridized, and so the carbocation is planar. That means in the second step, when bromine adds, it can add either to the front face, which will give us this product, or it can add to the back face, which gives us this product. So because of the carbocation intermediate, if a chirality center is produced, we will get a mixture of enantiomers. Next, let's take a look. Instead of reacting with HBr, what if we react an alkene with Br2? This is often carried out in some inert solvents such as dichloromethane or chloroform. And in the case of ethylene, this can react with bromine to give this product. And I did not save myself enough room. We can also carry out this reaction with chlorine, and in this case, we are going to make this product. Now, what if we have an unsymmetrical alkene? Well, in this case, because we are adding bromine to both of them, there is no issue of regiochemistry. The regiochemistry is irrelevant. But what about stereochemistry? If this behaved like these reactions, then we would expect that after the first bromine adds, we would get a carbocation, and then the second bromine would add to either the top face or the bottom face. However, what's observed experimentally, if we have cyclohexene and we carry out this reaction with bromine, we will make the trans product as a mixture of enantiomers. Now, if this proceeded by the same mechanism that we saw up here, then we would have one bromine. Let's say if a bromine became connected to the front face, we would have a carbocation at the other position, and then the second bromine would add either to the front face or the back face at this position. And while this new chirality center would have some influence on the formation of the second chirality center, we do not see any product that would have the two bromines cis to each other. The bromines add trans. Therefore, this cannot proceed by the same mechanism that we saw up here. So there must not be a carbocation intermediate. Now that we know what doesn't happen, before we look at what does happen, let's just look at a few other examples. Once again, if ethylene reacts with bromine, we are going to make dibromoethane, and this is a vicinal dihalide, so the halogens are connected to adjacent carbons. They're in the same vicinity, they're on adjacent carbons. If ethylene reacts with chlorine, we are going to get some of this. If ethylene reacts with iodine, we get junk because the products that form revert back to alkenes. It's kind of a messy reaction. So iodine is not used. And finally, If we carry out the reaction with fluorine, we get an explosion because fluorine is too reactive, and so once again, this reaction is not carried out. So we will focus then on reaction with bromine and chlorine. Let's look at a few more examples where we are sticking with chlorine, but now we are looking at different alkenes. So this alkene is unsubstituted, this one is disubstituted, and this alkene is tetrasubstituted. All of them will undergo reaction. Keep in mind, I'm not trying to show anything about stereochemistry here. They all will undergo reaction to form vicinal dichlorides. But what's also observed is that this reaction is the fastest, and this one is the slowest. So what this shows us is that the most electron-rich alkene reacts the fastest. So if an electron-rich alkene reacts faster than less electron-rich alkenes, that suggests that the alkene is still acting as a nucleophile. So it's similar to what we saw with reaction of an alkene with HX, where it is electrophilic addition, where the alkene shares electrons with an electrophile. So the alkene acts as a nucleophile, shares electrons with an electrophile. But there must be something different because of the observed stereochemistry. So the proposed mechanism then starts out the same as what we saw with other electrophilic addition. So this alkene will react with bromine. Now, with HBr, we had a distinct difference in electronegativity. So there was a permanent dipole. With two atoms of bromine, they have the same electronegativity, but still this molecule is polarizable. So the electrons can gather on one side or the other. Remember, this is the basis of London dispersion forces or induced dipole interactions. And so it could happen that this bromine takes on a partial plus and this bromine takes on a partial minus. So now we have an alkene that is willing to share its electrons, acting as a nucleophile, and we have an electrophile. So let's say this carbon steals the electrons from the other carbon and instead shares them with bromine. So it's a little bit hard to show that these electrons are going this way, and that pushes away the other bromine as a leaving group. But because this bromine has lone pairs, it can actually share electron density back again. So what does this give us? We still have our carbon-carbon sigma bond, and this is still connected to the hydrogens. But now this carbon has shared a pair of electrons with the bromine, and bromine has shared a pair of its electrons with the other carbon. The bromine still has two lone pairs, and we also have the other bromide leaving group. Now, bromine here owns 2, 4, 5, 6 electrons when it wants to own 7, so that means bromine has a positive charge. This intermediate is called a cyclic bromonium ion. A cyclic bromonium ion. So we do not have a carbocation intermediate as we saw with reaction of an alkene with HX. Instead, with X2, we have an intermediate cyclic halonium ion, and this is the key intermediate. Actually, I need to rewrite this, and let's show some stereochemistry. So let's turn this on its side, so that we're not looking at it planar in the screen, but instead the plane is perpendicular to the screen. And now we can see that this face is blocked by the cyclic bromonium ion. So that means when the other bromine comes back and attacks, it has to add to the opposite face. In this case, because these carbons are equivalent to each other, it doesn't matter whether it adds to the carbon on the left or the carbon on the right. But since the cyclic bromonium ion is on top, this bromine has to add from the bottom. So when this bromine takes its lone pair and shares it with this carbon, these electrons will move on to the bromine. And what does that give us? So here are our carbons, and here are the hydrogens. This bromine has its two lone pairs, and another lone pair is what used to be shared between the carbon and the bromine. And then on the other carbon, we have a hydrogen back, a hydrogen forward, and then the second bromine that added. And so because of the existence of this cyclic bromonium ion, the mechanism involves anti-addition, which would lead to a trans product. The trans is irrelevant when we don't have a cyclic structure, but this intermediate is important to explain the observed stereochemistry. Now, is this proposed mechanism consistent with experimental observations? So one of the things that we saw is that a more substituted alkene reacts faster than less substituted alkenes. So the more electron-rich alkenes react faster. This makes sense because the more electron-rich the alkene, the better able it is to share electrons with an electrophile. Another way to think about this is that when we have our cyclic bromonium ion intermediate, bromine has a positive formal charge, but because bromine's more electronegative than carbon, it will be pulling away electron density, forcing the carbons to take on a partial positive charge. The more substituted the carbons are, so if they have alkyl groups rather than just hydrogens, the more that partial positive charge can be stabilized, which is going to make this intermediate more stable, and therefore the transition state leading to it will be more stable, allowing the reaction to proceed more quickly. Perhaps even more important in terms of experimental observations is the trans stereochemistry resulting from reaction of cyclohexene with bromine. So if we think about the intermediate, if the cyclic bromonium ion forms on the front face, then when the second bromine adds, it has to add to the back face, opening this up here. And so this bromine is behind, and this bromine that was the cyclic bromonium ion is in front. Let me draw this again. If the second bromine added still from the back face, but to the top carbon, then this would still open up, and that would give us this bromine is in front, and this bromine is behind. And so we get a pair of enantiomers. Also keep in mind that the cyclic bromonium ion could form on the front face, as shown here, or it could form on the back face. If it forms on the back face for this particular molecule, it's the same thing. But it's important to keep in mind how the reactions can occur, what type of stereochemistry is possible, and therefore what is the stereochemical outcome. So the proposed mechanism that involves the formation of a cyclic bromonium ion, a cyclic chloronium ion, or more generically, a cyclic halonium ion, is consistent with both sets of experimental observations. Now, I mentioned earlier on that this reaction is typically carried out in an inert solvent, such as chloroform or dichloromethane, but what if you had water present? Well, what's observed is instead of getting a vicinal dibromide, what you get is this type of molecule, which is called a halohydrin. So what's going on here? The first part of the mechanism is going to be the same, where the alkene shares its electrons with bromine, and then the second bromine leaves, the first bromine attacks back, and we get a cyclic bromonium ion as an intermediate. Now, if there's only inert solvent, then the next thing that would happen would be attack of the Br minus that just got kicked out. But in this case, we also have present water. Now, if water is our solvent, that means we have many molecules of water compared to every Br minus. And so just thinking about probability, it's quite likely that water will bump into the cyclic bromonium ion. Water has to add from the back face because the cyclic bromonium ion is on the front face. So if water adds here, that will push open the cyclic bromonium ion, giving us this with our bromine forward. And then here we have water that added from the back. Oxygen still has one lone pair, and there is a positive formal charge on the oxygen. Finally, another molecule of water can act as a base and grab off one of these protons, put these electrons back here, giving us our halohydrin product. So here you are offering different nucleophiles that can add to the cyclic bromonium ion. The bromine and the nucleophile that opens the cyclic bromonium ion are connected to opposite faces of what used to be the alkene. So here we have halohydrin formation. So we saw that with halohydrin formation, the stereochemistry would be the same as when we formed our dihalide. In other words, we had anti-addition leading to the trans product. But when we form a halohydrin, there could be a difference with regiochemistry. So for example, if we start out with an unsymmetrical alkene that's also cyclic, we could get the bromine adding here and the OH trans to the bromine, or we could have the OH connected here and the bromine trans to the OH. When we had bromine and bromine or chlorine and chlorine, the regiochemistry didn't matter. But in this case, it does make a difference. So let's think about the intermediate that results from the first step, and we will make the cyclic bromonium ion. Let's say that cyclic bromonium ion forms on the back face, and we get this. Next, when water adds, is it going to add to the top carbon or to the bottom carbon? Because in this case, it does make a difference. Well, even though we draw the cyclic bromonium ion like this, we know that actually bromine is stealing electron density so that this carbon has a partial plus, this carbon has a partial plus, and bromine, instead of having a full positive, it also has a partial plus. But more specifically, this is not necessarily an equilateral triangle. Whichever carbon can better bear the positive charge, that's the one that's going to have more positive character. So if we have a carbon that's connected to a couple hydrogens compared to a carbon that's connected to a couple of other carbons, we know that carbons are better able to share electron density to stabilize a carbon that has a partial positive charge. Whereas hydrogens, even if they want to try, they can't help this carbon very much. So that means that this cyclic bromonium ion is really going to be more skewed like this. So we still have a formal charge on bromine, but because it's pulling electron density away from the carbons, it will have a partial plus. This carbon will have a little partial plus, and this carbon will have a bigger partial plus. because it has more help to be able to stabilize that, to be able to spread out that positive charge. But now these carbons are not equivalent to each other. So when water is looking for an electrophile, it sees this as a much more electrophilic atom compared to this one. So water is going to selectively add to this carbon, leading to the cyclic bromonium ion opening up this way. That will give us the protonated halohydrin, and then after proton transfer, that gives us this product. So when we have an unsymmetrical alkene, the water is going to add to the more substituted carbon because that is the one that has more positive character. So we can think of it along the same lines as Markovnikov addition, where the nucleophile adds to the more stable carbocation. Well, here we have the nucleophile adding to the more stable almost carbocation, leading to this product. Please note that even though I drew the mechanism this way, where the cyclic bromonium ion formed on the back face, it is equally likely that the cyclic bromonium ion will form on the front face. If that happens, then when water adds, it'll still add to this carbon, but this methyl group would be back while the cyclic bromonium ion is in front. And then when water adds to this carbon, that is going to give us the enantiomer of the product I've drawn here. So this reaction is stereospecific, where we get the trans product, not the cis product. It is regioselective, where the OH becomes connected to the more substituted carbon, but we still get a mixture of enantiomers. Now, as we learned in lab, working with bromine itself is not really ideal, and we're using water as our solvent, but a lot of alkenes are not going to be soluble in water. So in practice, we kind of have a problem. On paper, no problem. We can write this reaction this way. But in practice, there are many other reagents and different conditions that have been developed to be able to carry out this reaction more efficiently, in a more environmentally friendly manner, for example, more safely. So one of these is shown here, and here we are using N-bromosuccinimide, NBS. So this is N-bromosuccinimide, and it is a source of Br2. So the chemist will measure out NBS, add it to the reaction, and the NBS will form Br2 in situ. Rather than just using water, we can use DMSO, dimethyl sulfoxide, as our solvent. So this is the structure of dimethyl sulfoxide, a very commonly used solvent. And all we need is a little bit of water to be able to act as our nucleophile once we have formed our cyclic bromonium ion. So we have water and DMSO as co-solvents. We have an alternative source of bromine, and that makes this reaction a lot better. Still leading to the same product as above, this compound as a pair of enantiomers.